Good afternoon. Today is Tuesday, October 13th. This is a follow-up video on water and pH. So I want to share with the virtual students some of the background information I gave in class. So I'm going to share my screen with a whiteboard, which doesn't work the best, but I think we can make it work. So water, H2O. Why is it H2O? Well, it has to do with the atoms being stable that form water. So I'm going to assume that you understand what an atom is, and that an atom contains a nucleus made of positive protons and neutral neutrons. And that pretty much stays together at all times. It's the number of protons that gives an atom its identity. That's its atomic number on the periodic table. And then orbiting or circulating or moving around this nucleus are the negative subparticles called electrons. For biology, that's the part we are most critically interested in because it's the electrons that are involved in forming chemical bonding. So if you look at the drawing of an oxygen molecule, do a little thing. If you go onto the periodic table, oxygen is going to be atomic number 8. That means there are 8 positive protons in oxygen. So that means how many electrons do you have to have? Well, atoms are typically neutral. So if you have 8 positive protons, you need 8 negative electrons. But there are rules on how you arrange those electrons, which you may or may not already be familiar with. So this first orbital, which I'm trying to draw a dashed circle, but not very well. This first orbital has rules. And the rule is you can fit a maximum of 2 electrons around the first orbital. So it's got 8 electrons, so it certainly can put 2 electrons, 1 electron there. Let me use a different color so it stands out better. So we got 1 electron right here. Come on, just give it to me. There we go. That's too thick. And then we've got another electron right here. I just randomly place them. So there's 2 electrons on the first level. That's maximum capacity. And these electrons are attracted to the positive nucleus. That's what sort of keeps them in an orbit around the nucleus, almost like the gravitational pull of the sun with the planets. That's what keeps the planets around the sun in an orbital. It's the gravitational pull. Here, it's the electrical attraction between the negative electrons and the positive nucleus. So then we have to move out to a second level. And again, this is not a very good representation of a dashed circle. And there are rules about the second level. The second level can hold 8 or 18 electrons. 99% of the time in biology, we're going to be dealing with 8, but the rule is it can hold 8 or 18 electrons. So you got 2 electrons on the first level, so 8 subtract 2, that leaves you 6. So I can put 1, 2, and I'm just randomly placing them, 3, 4, 5, 6. So now that is chemically neutral. 8 positive protons, 8 negative electrons. So if I ask you the question, is this a neutral atom? The answer would be yes. Is this a stable atom? The answer would be no. This is not a stable atom. To be stable, you have to have your outermost layer of electrons complete. So there is only 6 in the second layer, but you can hold up to 8. So this atom needs to either get rid of 6 electrons, or it needs to find and gain 2 more electrons. Typically, the smaller number is the easier task. So finding 2 electrons is going to be what the oxygen atom is going to try to do. So thus we bring in hydrogen. Let's make hydrogen a different color. And so hydrogen, if you look at the atomic number, hydrogen is atomic number 1. And if we get our orbital around here, These are the worst orbitals. How many electrons are you going to have if you have one proton? Of course, yes, you're going to have one electron. Now, hydrogen, is it balanced? Yes. Is it chemically stable? No. It either needs to lose that electron or gain an electron. There's also one other option. It can share the electron. So when you're gaining and losing electrons, that's when you're going to get into this type of bonding called ionic bonding. When you share electrons, you get into the much stronger bond, which is called covalent bonding. And so the hydrogen is going to share this electron with the oxygen. It has to do with a property called electronegativity. As you go from the periodic table from the right, which hydrogen is on the far right, all the way to the far left, where you find oxygen and fluorine as the farthest left, excuse me, the farthest right. So if you go from left to right, hydrogen's on the left and fluorine, oxygen on the right, the electronegativity increases as you move across the periodic table. The electronegativity has to do with how strong a pull the nucleus has on the electron. So something with low electronegativity, such as hydrogen, has a very weak pull on the electron. Something like oxygen and fluorine, which are atomic numbers 8 and 9, their nucleus has a very, very strong pull on the electron and has a higher electronegativity. So the result is this electron is going to be more strongly pulled towards the oxygen nucleus than towards the hydrogen nucleus. So this electron is going to literally, what happens because you're sharing the electron, it will spend part of its time circulating the hydrogen atom, but then it will also spend part of its time going around the oxygen atom. And because the oxygen atom has a stronger electronegativity, the electron will spend more time circulating the oxygen than it will the hydrogen. Not to also mention it's slightly physically bigger. So now, when we ask the question, is the hydrogen stable? Yes, because it's considered to have 2 electrons, because it'll share some of oxygen's electrons along with its own electrons. At any one given moment, you'll typically find 2 electrons orbiting the hydrogen. Thus, it'll be considered more stable. However, is the oxygen stabilized yet? So now it's got 1, 2, 3, 4, 5, 6, 7 electrons, but it needs 8. So how does it get another electron? Well, one way is to get another hydrogen. So if we take another hydrogen, atomic number 1, and we introduce another hydrogen into this story, we are going to be able to complete the balance. So here's that electron. It's going to also be shared, which means it'll spend some of its time going around the hydrogen, and it'll spend some of its time going around the oxygen. Around the hydrogen, around the oxygen, around the hydrogen, around the oxygen. As a result, because the electrons are going to spend more time around oxygen because of the big discrepancy in electronegativity, the oxygen is going to have, let's pick a different color here. The oxygen is going to be slightly, or we say partially negative, because at any given moment, there's more electrons than there are protons. At any given moment, there might be 9 or 10 electrons to 8 protons, and thus it's slightly negative. Same thing on the hydrogen. At any given moment, it's probably going to be no electrons, which would make this partially positive. And so the hydrogens take on a partially positive charge, the electrons take on a partially negative charge. This creates the unique properties of water. This is what creates what's called a polar covalent molecule. Covalent because the hydrogen and the oxygen share electrons, creating covalent bonds, and polar because you are polarized. You have a separation of charge. You have one end of the molecule that's positive, and the other end of the molecule is negative. That's what we mean by polarized, so polar covalent. And because of this molecule being polar covalent, it can do what's called hydrogen bonding. And hydrogen bonding is what gives all of the water its unique properties. So it gives all the water its unique properties. So that's the first step. Let me clear this. So then you did the activity about properties of water. And because of this hydrogen bonding, there's surface tension. Water likes to stick to itself. There is high heat of vaporization. Water molecules, because of these hydrogen bonds, it takes more energy investment to get them to break those hydrogen bonds and make a phase change. So water can absorb more energy gram for gram than any other liquid, because you have to first invest energy in breaking those hydrogen bonds before it makes a phase change into a gas. One practical example, or one practical use of that, is it helps us cool our bodies down. You sweat, you put water on the surface of your skin, and water absorbs the heat from the body, and it absorbs tremendous amount of heat, gram for gram, and therefore then a phase changes, evaporates, and pulls lots of heat away from the body. Where if you remember alcohol, when you rubbed it on the table, disappeared almost immediately. If you sweat alcohol, you'd never be able to cool down. It doesn't pull enough heat. Also in the lab, they talked about, we compared a beaker of water to a beaker of oil. The beaker of oil temperature went way up compared to the beaker of water because that's high heat capacity. Water can absorb a lot of heat before it raises temperature and goes through a phase change, because all that energy is being absorbed in those hydrogen bonds. And so it makes water a good heat sink. That's why temperatures are almost always cooler along our coastline. That's why Port Huron most of the time is 10, 20 degrees cooler than St. Clair. That big Lake Huron sucks up a lot of heat and holds on to it, regulating the environment. And many other properties like capillary action, being a universal solvent, all those things relate back to hydrogen bonding. Well, during all reactions require water. They all require water. So it's 2 hydrogens and it is 1 oxygen. That's what makes it chemically stable and balanced. Well, during every chemical reaction, some of the water, almost every reaction in your body requires water. And during those chemical reactions, water does what we call dissociates. It splits into 2 ions. And what you end up with is hydrogen ions, H+, and you end up with what's called hydroxide ions. Which carries a negative charge. And those are the 2 ions that you create. And pH is parts of hydrogen. It measures how much hydrogen is in the environment. So the more hydrogen you have, the more acidic it becomes. Vice versa, the more hydroxide you have, the more basic it becomes. So during the reaction, water dissociates a small amount. And depending on the reaction might consume some of that hydrogen, or it might consume some of those hydroxides. So if the reaction consumes some of those hydroxides, but not the hydrogen, at the end of the reaction, you're going to have leftover hydrogen. The leftover hydrogen stays in the environment, causing the pH to drop. Or vice versa, if you end up with leftover hydroxides at the end of the reaction, they're not consumed during the reaction. Those extra hydroxides are going to raise the pH and make it more basic. And that's the basic idea. So you may recall pH scale, basically 1 through 6 is an acid, 7 is neutral, and 8 through 14 is considered alkaline or base in that. The way this works is it's based on the exponent. So something with pH 7, you have 10 to the negative 7th hydrogen ions. You have 10 to the negative 7th hydrogen ions. The negative 7, the exponent there, is how we get the value pH 7. You have 1 times 10 to the negative 7, so 0.000001 hydrogen ions. In a neutral solution, you also have 10 to the negative 7th hydroxides. But the value is based on the pH, not the hydroxides. So it's neutral in this case because you have equal amounts of hydrogen and equal amounts of hydroxides at the end of this chemical reaction, which means most of them are simply going to join back together and form water, thus no pH change. The other key is these two exponents will always add up to 14. They'll always add up to 14. So if you have something that say is pH 3, that means you're going to have 10 to the negative 3rd ions of hydrogen, which means if that's the case, hydroxides are going to be 10 to the 14 minus 3, 10 to the negative 11th hydroxides. So 0.001 hydrogen, 0.00001 hydroxides. So this is a much more acidic solution. This would be something that has a pH of 3. You always go by the exponent of the hydrogen content. This is a pH of 7. If we had something that had, say, a pH of 10, something that's more alkaline base, that means that we have 10 to the negative 10th of hydrogen. We have a very small amount of hydrogen. Very small amount of hydrogen. Most of the solution is going to be 10 to the negative 4th, a much higher concentration of OH, making that a very strong base. Okay. So pH value drops when you become more acidic because the exponent gets smaller, which means the concentration gets larger for the hydrogen concentration. The other key thing that I'll point out on pH is that the difference between pH is 10-fold. Each level is a 10-fold change. Because if I go to pH 6, that's 10 to the 6th. That's a 10-fold change. So if I go from 7 to 3, that is a 10 to the 4th change. That is a 10, pH 3 is 10,000 times more acidic. 10 to the 4th is 10,000. So pH 3 is 10,000 times more acidic than neutral. That's why nothing living is going to live. Very, 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 very few things are going to live in a pH 3 environment. In most rivers and streams, if you drop down below 5, you're going to kill pretty much everything in the river or stream. So when we say you shift from pH 7 to pH 6, it's a big deal. It's 10-fold increase. Going from 7 to 5, that's a 100-fold change. Of course, that's going to kill most everything. Same thing going this way. Something with a pH 10, right? It's a 3-fold difference. The neutral solution is 3,000 times more acidic than something with a pH 10. So I'm hoping that makes a little bit of sense to you. And in the lab, we'll come back to, the key is we got to keep that pH relatively stable. If you don't have a stable pH, those extra hydrogen ions and or extra hydroxide ions, they interfere with protein folding, which denatures the protein, destroys your enzymes, and now your body can't function. So pH is really critical. It's right up there with temperature. It's got to be maintained. And in the lab, we explore the ideas of these things called buffers, which will help us counteract the changes in pH. So that's a little bit about water and pH that might fill in some gaps. Thank you for your time. We're going to sign out of this one and make another one here in just a moment. So I'm trying to get out of here. Okay, beautiful.